Acid and base equilibrium review, real-life application, and an example question. So we know that Ka is the acid dissociation constant, which relates to acid strength. The pKa value is the negative base 10 logarithm of the acid dissociation constant, Ka, of a solution, which is this formula, in red. From this formula, we can see quite obviously that the smaller the value of pKa, the stronger the acid will be. pKa is used normally because the value is easier to use in calculations because Ka is usually really small and therefore harder to use in calculations. So this is why we use pKa over Ka sometimes. So as we learned in class, there are three main theories about acid and bases, and we use a combination of them when learning about acid and bases. Arrhenius' theory discusses acid and bases as ions. When dissolved in water, an acid produces hydrogen ions, and a base produces hydroxide ions. Just as a reminder, an acid and base react together and neutralize, creating a salt and water, in this case, sodium chloride. The second theory we learned is Bronsted-Lowry's theory, which states that an acid is a proton donor and a base is a proton acceptor. This is where we learned about conjugate acid and base pairs that differ by one hydrogen ion. So when acid is dissolved in water, water will act as a base and accept a proton from the acid, resulting in the formation of the conjugate base of that acid and a hydronium ion. The reverse happens when a base is dissolved in water. Water will act as an acid and will donate a proton to that base, which will form the conjugate acid for that base, and will deprotonate water, forming hydroxide ions. The final main theory we discussed was the Lewis acid-base theory that focuses on electron transfer. The Lewis acid is an electron pair acceptor, and the Lewis base is an electron pair donor. So for a Lewis acid-base reaction, the base donates a pair of electrons to the acid. This is it for the review of what we discussed in class. Now I will go into a real-world application. So we have all heard of acid rain, and I'm sure you've learned before that it is an acid-base reaction. But I'm going to go into more detail about this reaction and how we have developed a way to neutralize the rain in areas that need it. This diagram gives a really well-detailed visual of how acid rain occurs. We can see how the acids and bases and neutral aerosols come together, and we can see the anions and cations. Acid rain starts when an unpolluted atmosphere receives acidic, basic, and neutral substances, sometimes from natural sources, but now quite often from pollution. The substances react in the rain to cause a gigantic acid-base titration or a neutralization reaction. The hydrogen ions must predominate to maintain charge balance when this occurs. Carbon dioxide is the main source of acidity for normal unpolluted atmospheres. It dissolves in water to form carbonic acid. Naturally, all rain is acidic with a pH of 5.7. Acid rain is defined as rain whose pH is controlled by pollutants that lower the pH to the 3-4 range, causing severe damage to the environment. Emission of sulfur dioxide and various oxides of nitrogen, which are known as NOx substances, are the main sources of acid rain. These typically come from combustion processes, the big one being coal burning. Acid rain harms many things, the main ones being plants, soil, water ecosystems, and buildings. This is one of the reactions that occurs for acid rain. Sulfur dioxide reacts with oxygen in the air to create sulfur trioxide. Sulfur trioxide then reacts with water and rain to form sulfuric acid, which we know would greatly impact the pH of rain. It would take many more steps, but later the sulfuric acid would be dissolved in water and the water would act like a conjugate base and would later create the conjugate base and H3O+, which we know is a conjugate base and acid example. One way society has figured out to neutralize rain is by introducing calcium carbonate into the atmosphere. It will react with the sulfuric acid to form calcium sulfate, water, and carbon dioxide. Calcium carbonate actually doesn't hang out long in the atmosphere and is one method they have additionally discovered and are researching more because it has potential to hold carbon dioxide and prevent large amounts from going into the atmosphere, causing global warming. Acid rain is dangerous, and many countries around the world have banned combustion processes, like coal burning, to prevent not only global warming, but acid rain. Now we will do an acid-base equilibrium example. If nitrous acid has a Ka value of 4 times 10 to the negative 4 at 25 degrees Celsius, what is the percent dissociation of nitrous acid in a 0.4 mole solution? The first step is to create and balance our equation of the reaction, shown here. We can see our weak base, nitrous acid, and how it reacts with water to form hydrogen and nitrogen dioxide. Second step is to set up our Ka expression by putting the products on top divided by the reactants, remembering not to include water in that. Altogether, that will equal our Ka value. Now we can set up our ice table, as you can see here. Now that we have our X values for each substance, we can fill it into our Ka expression from earlier. When we simplify that Ka expression, we see that it is a quadratic equation, and solving that, we find X equals 0.0126 moles, and we know from our ice table that X equals the values of nitrogen dioxide and hydronium. Now that we have the mole values for those solutions, we can plug them into our percent dissociation formula, having nitrogen dioxide divided by nitrous acid solution mole value. So 0.0126 moles divided by 0.4 moles, and then times that by 100. We get 3.2% as our percent dissociation value. So therefore, the answer to our question is 3.2% of the nitrous acid has been dissociated into hydrogen and nitrogen dioxide ions. So for our second example of an acid-base equilibrium, we're going to try and find the pH of a 1.5 mole solution of ammonia, NH3, at room temperature. So our first step is to find the balanced ionization reaction, and we can see it here. Next, we have to do the Kb expression, so we can fill in with the reactants on top and the products below. Just a reminder again that we don't include water in this expression, and we can all set that to equal 1.8 times 10 to the negative 5. Then we can create our ice table. So we put in our 1.5, and we know that minus X will equal that, and then so NH4 and OH will be equal to X. Then again, we just do our Kb, we fill in our X's, and then we can simplify that to be X squared over 1.5 minus X equals 1.8. And then when you solve that, X will be equal to OH, and it'll equal NH3, and then that equals 5.2 times 10 to the negative 3 moles. So now we just need our OH because we need to solve for the POH. And so POH equals negative log OH, and we can solve for that, and you get 2.28. And now we know that pH and POH at 25 degrees Celsius, or room temp, equals 14. So we can set it up to solve for the pH, and that equals 11.72. So therefore, the pH of a 1.5 mole solution of ammonia at room temperature is 11.72. Thanks for watching my tutorial, and good luck on exams.